In this module, we shall give a complete description of every single compact subset of R. Without further ado, let me state the theorem. Heine-Borel. A subset K of R is compact if and only if it is closed and bounded. And the proof is rather easy. An unbounded set cannot be compact. This we saw in the previous module as an example of non-compact set. If a set U subset of R is not closed. In the last module, one of the examples was that saying that any open set U would be non-compact. An open set cannot be non-compact. Now I'm starting with if a set U subset of R is not closed, then it must immediately be not compact, right? Because a set that is not closed must be open. No, this is not true. This is not true. One of the common mistakes beginners make is to have this false dichotomy that a set that is not open must be closed and a set that is not closed must be open. The complement of a closed set is open and the complement of an open set is closed. Does not mean that any set that is not open is closed and vice versa. A subset of R, just like a door, can be open, closed, or anywhere in between. So please remember that. So I cannot just say since set U is not closed, it must be open, we are done. No. If a set U is not closed, then there is a limit point X in R of U such that X is not in U. That's the only way by which the set U can fail to be closed. It has some limit point which is not there in the set. Let Xn in U be such that Xn converges to X. Such a sequence must exist simply because X is a limit point of U. But no subsequence, or rather I will not want to have too many negatives, but every subsequence of Xn must converge to X. Hence, U is not compact. The definition of compactness is that every sequence in that set has a subsequence that converges to a point in that set. I have considered a point outside that set and found a sequence that converges to that point. No subsequence therefore can converge to a point inside that set. So the definition of compactness is violated. Okay, so we have proved one direction. We have shown that if a set is compact, then necessarily it has to be closed and bounded. Now let K subset of R be closed and bounded. We have to show that it's compact. And the proof is exactly word for word what we did for a closed interval. Let Xn in K be any sequence by Bolzano-Weierstrass. Xn K converges to some X in R for some subsequence. By closeness, X is in K. And we are done. This is word for word the argument we gave for a closed interval. So this short proof completely characterizes compact subsets of R. They are precisely the closed and bounded sets of R. Now, there can be many exotic compact sets. We will explore one of them in a later module called the Cantor set. You must not be misled into believing that the only compact sets look somewhat similar to closed intervals or finitely many points. They can be very complicated. The Cantor set is one exotic such object which we will discuss in some detail. Now, the last part of the proof of the Heine-Borel theorem sort of suggests that even though compact sets could be very weird, they do behave very much like closed intervals in a lot of senses. Okay, this analogy that closed sets, closed and bounded sets are similar to closed intervals can be illustrated in another theorem. Nested intervals theorem for compact sets. Remember, we had a nested intervals theorem for closed intervals. I was about to write compact interval. That makes no sense. Compact sets. Okay. The theorem is as follows. Let Ki or Kn, n in n, be a sequence of nested intervals. This just means that Kn is a subset of Kn minus 1, the subset of Kn minus 2, dot 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 is a subset of K1. The sets are all nested inside each other. Okay, like a Russian doll. Suppose, no other assumption is needed. Be a sequence of nested, I wrote intervals again, sorry about that. Be a sequence of nested compact non-empty sets. I don't want any of these sets to be empty. Then intersection Kn is not the empty set. Okay. In fact, intersection Kn would be, I will talk about that in later. Let me just finish off with this. Intersection Kn is non-empty. Proof. What I do is the following. Let Xn be in Kn. Since each one of these sets is non-empty, by assumption, by a hypothesis, I can find an element Xn in Kn, right? Let Xn in Kn. Note that Xn such that n greater than or equal to some m is a subset of Km, right? Why is this? Because these are nested intervals. So in particular, this entire Xn is in K1 for all n. Okay. So all the terms of this sequence beyond the mth term will be a subset of Km. Now, by compactness, some subsequence of Xn converges to X in K1, right? Now observe that by deleting the first suitable number of terms, in the subsequence, we get a subsequence in Km, okay, here M is fixed, okay, that subsequence will depend on M. In fact, if we delete the first M minus 1 terms of the subsequence, we get a subsequence in Km. So at the most, the first M terms can be M minus 1 terms can be outside of Km. Okay, so this means this new subsequence also converges to X. I've just deleted the first few terms of a subsequence. The resultant subsequence should also converge to X. Therefore, X is in Km, again by compactness. Within a compact set, if you have a sequence that converges, that point at which it converges must be in K, right? So that means, this means X is in intersection of Kn, and we are done. So this nested intervals property generalizes to a nested intersection theorem for compact sets. This is a course on real analysis, and you have just watched the module on the Heine-Borel theorem.